In this lecture, I am going to show you how to solve for problems where you're determining the empirical and molecular formula from data. See, we've already learned that we can do different types of chemical analysis and procedures where we can drive away, let's say, um, oxygen from sodium oxide, and we can determine the percent of the sodium that's remaining. So there's different ways we can find the percent by mass of different elements. One way we've determined, or one way we've utilized this, is we've taken a hydrate at this point, which is nothing more than a salt that has a particular amount of water locked into the crystalline structure at distinct ratios. And with heat, we have made the anhydrate, the dried compound, and the water went away. We found the percent by mass of water that way. So we've already done procedures where we've determined the percent by mass of different components of a compound. Now, once we do those types of procedures and we know the percent by mass of each of the elements, what we can do now is start building chemical formulas. Pretty cool. Analytical chemistry is what we do is when we basically take samples and we do chemical analysis to figure out what they are. One way to do that is to determine the percent by mass of all the elements in the component, or in the compound I should say, and then take those percentages to build something called an empirical formula. Now, an empirical formula is the lowest ratio. We've already dealt with empirical formulas. This is the lowest ratio of elements. Now you say, well, why the lowest ratio? Well, if you're dealing with percentages and you know nothing else but the percent by mass of each component already determined from other chemical types of analysis or procedures, all we can ever come up with is a ratio of elements. We don't know the exact number that could exist in nature. All we know is the lowest ratio. But what I will tell you is that if the compound is ionic, for instance, I see a metal here, sodium, sulfur, and oxygen, this is giving me the idea that this might be an ionic compound with the presence of a metal in the compound. If something is ionic, ionic compounds make crystals, and those ionic compounds can only have the lowest ratio of ions. Remember, because if you've got a positive and a negative ion, all right, they're going to go in 3 dimensions, and in 3 dimensions you're going to build a crystal lattice, a regular repeating structure of ions. No one's going to count the total number of ions, but what you will have is the lowest ratio of them to build a crystal. So ionic compounds are always empirical by nature. All right. Now there's another word that's going to pop up in this lecture, and that's the word molecular. So molecular formulas are not typically lowest ratio. Empirical or for ionic, molecular have a long time been for covalent compounds. As you probably already learned, covalent compounds do not make crystals. They make exact particles with an exact number of elements, okay, that make up the ratio. For instance, H2O is a compound with 2 H's bonded to 1 oxygen, as you probably have already learned. So that's a compound, and that's its molecular formula. Just so happens that water exists already in the lowest ratio, a 2-to-1 ratio. So water is an example of something with a molecular and an empirical formula. Now, if you look at something else, let's look at hydrogen peroxide. Hydrogen peroxide, its Lewis dot diagram looks something like this. I call it the sunglasses. Okay, it's got a bent structure, not really drawn that well, so I'll give it another whirl. All right, so if you look at something like sodium hydroxide, where you have 2 O's, hydrogen peroxide, and you've got 2 lone pairs up top, and it kind of bends this structure down. Okay, I got 2 lone pairs as well here. Okay, you'll see that this is H2O2. Well, this, my friends, is a molecule. This is the actual particle that makes up this compound. So its molecular formula, okay, which is the formula of how the molecule exists in nature, okay, is H2O2. Now, it's empirical, which is what we would find in lab, because if you're using percentages, you don't know exactly how many of each, you just would know the lowest ratio. To find a percentage, percentage is part over total. Again, you have no idea of multiples. All you would come up with is the lowest ratio. So the empirical formula that we would find in lab for hydrogen peroxide would be HO. Ho, okay? So HO is the empirical, the lowest ratio, which is the empirical formula of this molecule. And of course, the molecular is the actual numbers that exist in the molecule. So empirical is the lowest ratio. Molecular formula, okay, is the one that actually exists in nature. Case in point, we'll do one more. Glucose, C6H12O6, exists in nature as a molecule with this ratio, 6 to 12 to 6. That's the actual number of atoms that exist in this particle called a molecule. But if I reduce glucose to the lowest terms, I would get CH2O. It's a 1 to 2 to 1 ratio. And this is what we would find in lab for building empirical lowest ratio formulas. Okay? Just keep in mind, just like water, as I talked about, there are elements that can already exist in nature in their lowest ratios. So water is an example of a compound that exists both in its molecular formula, how it exists in nature, exactly like this molecule, and is also in its lowest ratio. So water, H2O, is both a molecular formula and an empirical formula. So a little lesson there. Now, let's step back and let's actually solve for how we actually start to build chemical formulas. So what we're going to do is we're going to take the percent by masses that we've already gotten from previous chemical procedures, and using these percent by masses of our unknown compound, let's say white powder, okay, I waited for it, we're going to now build an empirical formula. We can only build lowest ratio formulas from these percentages. Again, this is only percentage is not built on exactly how many, it's part of a total. So I'll never know what the molecular formula is of a compound just by this procedure. Just build the lowest ratio. However, if it's ionic, it'll build a formula exactly. So let's just get started. So the first thing I'm going to do is write the percentages down. I have 36.5% sodium. I have 25.4% sulfur. And I have 38.0% oxygen. Okay. So again, this could be from a 1,000-gram sample, this could be from a 550-gram sample, this could be from a 1-gram sample. Don't know, don't care. What I will do, though, to make life easy, the first step, or the first thing I want to think is I'm going to make an assumption. And I know when you make an assumption, you make a donkey out of you and me. I'm going to assume a 100-gram sample. Now I can assume any 100-gram sample. Okay, I can 1,000-gram, 55, but I'm going to make my life easier. If I got a 100-gram sample, I know that 36.5% out of 100 is 36.5 grams. Same thing, 25.4% of sulfur, or 25.4% of 100 is 25.4 grams. By assuming 100 grams, the percentages that were given to me based on some unknown amount, okay, now can be linked right into grams. So this becomes 36.5, okay, grams of sodium. Name is Mr. Grodsky. Why do I want to go to grams? Well, guess what? If I'm building a chemical formula, which is a ratio of what? Elements, but ratio of what? How many? You might have already guessed, I want to get into moles. Moles, as we've already discussed at length, ad nauseum, is a how many number. So I know that I can convert my grams into moles. First step is take my percentages. So again, my sulfur, assuming 100 gram sample, 25.4% of 100 is 25.4 grams of sulfur. And same thing here, 38% of 100 is also 38% or 38 grams. I can do this, okay, of oxygen. So now that I got my grams, and that's something I needed, I can convert my grams into moles. And that's very important. And you find yourself in a problem and you don't know what to do. They always say in chemistry, if you don't know nothing to do, convert to moles and see what happens. But yeah, we're going to convert to moles here because we want to get to a how many number to get what? How many elements the ratio is to each other. So first step, convert to moles. Well, second step, I guess, now is converting to moles. And we'll change it up here. So I'm going to get rid of grams, dimensional analysis, and I want a mole. 1 mole is how many grams? Okay, if we look on the periodic table for sodium, it's 23. We're going to round off to 23. It's good enough. And let's get that number. And I get 1.58. Carry some numbers. Let's do 69. Okay, and now I'm going to do the same thing here. I'm going to convert my grams into a how many number so that I can figure out how many of each element that ratio is. And I know that sulfur is 32 grams per 1 mole. And let's go find that number. And I get 0.7937. Okay, same thing over here. Let's get rid of oxygen. Okay, 1 mole of oxygen atoms is 16 grams. Again, where I'm getting this is the atomic masses. Do not make this 32. This is not O2. We're doing individual atoms here. So these numbers that you're seeing me list here are the atomic masses. Okay, I don't like that, so let's get rid of that. All right, we should know how to convert to moles at this point. We've talked about that ad nauseum. Now, so 2.375 is the number of moles. Okay, now again, for those, I'm just canceling out my units to know that I have moles. And these are all moles. Okay, well, we can't build a chemical formula. Now that we've converted our how heavy to a how many, we can't use this number here and plug it into a chemical formula. That would make no sense. We can't have sodium 1.58 to sulfur. We can't put these numbers in, so we're going to have to come up with whole numbers. And the reason why we need whole numbers, well, because chemical formulas are built on whole numbers. And the reason why we discovered that atoms existed because, well, heck, there was what? There's 1 sodium to 1 oxygen in sodium oxide. There's never anything less than whole numbers. We found through experimental analysis that there's got to be a whole number ratio as long as our data is accurate enough. Okay, so we have to come up with whole numbers because atoms exist as whole numbers. So what we do from this point forward is we try to find that ratio. Again, I don't know exactly how many moles we have or how many because, again, these percentages are based on some number I don't know, and it doesn't matter. A percentage is out of some total. So what we're going to do here is we're going to divide by the smallest number to get that ratio. So I find that my sulfur is the lowest number, so I'm going to divide by 0.7937. If you notice, of course, I'm going to get a ratio of 1. Now, if you notice, I'm dividing mole by mole, and mole cancels, so these ratios are dimensionless. Okay? Any case, I'm going to divide this by 0.7937. Of course, I'm going to get a number, and that number, when you put it in your calculator, 1.5869 divided by 0.793, interesting enough, you get 1.999, which you can round off to 2. Why am I getting 1.999 and not exactly 2? Is because there's probably some what? Rounding going on here. in our data, or there's a little bit of error, okay? But you should get something close to a whole number. If I get a 1.5 here, I can't round off half an atom. These should come out, when you do these ratios, they should come out to almost exactly that whole number. If not, we have more work to do, and I'll give you that example, okay, as we go through. So last one, divide by, again, the smallest number. All we're doing is dividing by the smallest number. Like in class, if I wanted to know, hey, what is the ratio of heights in the room? You'd take my height, because I'm probably the tallest, and to find out who would be the smallest, who would be the standard, who'd be the one, okay, you divide by the what? The smallest person in the room, okay? So you divide by the smallest person to get that number 1, okay? Or at least you divide by, you take the smallest person, divide by itself, that gets to 1, and then you take me, and you divide by the smallest number to see how many multiples of that. Maybe it would come out to be 2 in some cases. Who knows? Okay, so in any case, 2.375, put this in our calculator, 2.375, and lo and behold, you will get 2.9923. 2.99 is essentially 3. Again, the reason why it doesn't come out exactly is because probably of some rounding, or some rounding in our what? Formula masses, okay? So that is why, and of course, if it comes very close, you're very, very confident those are the ratios. So what is the chemical formula of number 1? Well, I have what? I have 1 sulfur, 3 oxygens, I have 2 sodiums. Remember, if it's an ionic compound, which it appears to be because, well, I have a metal involved and some nonmetals, I can see that the Na is going to go first. I've got what? 2 of them, right? And then I'm going to put sulfur next. You may say, Mr. Grazzi, how do you know to put the sulfur next? Well, I'm thinking that this sodium, and I have what? 3 O's. Isn't this sodium sulfite? Isn't SO3 the sulfite ion, right, that we learned? Sulfite, ite because less O's. This is the sulfite ion, and naming this would be sodium sulfite. And this is the exact chemical formula of sodium sulfite. Now, why 2 sodiums? Because when you look up sulfite, it's a -2 charge for each polyatomic ion. Sodium is +1. So it makes a lot of sense that our answers for salt or something, what, ionic, would build the exact chemical formula that you would get if you put these elements together. So that's the empirical formula, which is the exact formula because it is a salt or it is ionic. Okay, so what I'd like you to do is on your own try number 2. And you're going to pause me right now. And when you pause me, give me a couple seconds and I will show you what I get. So pause me right now, stop me, try number 2. Okay, I'm back. Now, you probably already figured out that it's 1H to 1F. Using the percentages, assuming a 100-gram sample, making a donkey out of you and me, we convert these to grams, and then of course we determine the moles, convert to moles, and you notice we both get 5 what? 5 moles apiece. You didn't really have to divide by 5 here, but I'm just making sure you understand where I got it from. So a 5 mole to 5 mole would be a 1-to-1 ratio. And of course I put the H in front only because I know that normally the H is going to be the positive one and fluorine's a negative one, and when you look at building chemical formulas. But I also know that acids have an H in front. This is hydrofluoric acid, just from experience. If you put FH and didn't know, I'd still accept it. And by the way, this is an empirical formula. It's not a molecular formula, but in truth, it's also, HF does exist this way. But what you found was the empirical formula, okay? So I would love for you to continue on and do 3, 4, okay, 5. You're going to run into a scenario where when you get to the point where you find the whole number ratios, it's not going to work out perfectly. And please see what you have to do there. What may happen to you is, let's pretend I'm a princess and let's pretend that this 1 was really 1.5. So if this was 1.5 instead of 1, well, you can't put 1.5 in the compound, but what you can do is multiply everything by 2, and this would give you 4, right, times 2, and this would give you 3 and 6. So if you come to a scenario when you divide by the smallest mole and you get something other than a whole number, especially like something close to a half, like 1.5, you're going to have to do an additional, okay, manipulation to get whole numbers. Because if you think with me for a second, there are ratios that are what, 2 to 3. Isn't that really 1 to 1.5 when you do it this way? So you're going to have to multiply what? Everything by 2 to get those whole number ratios. So not everything is going to be an even ratio, so sometimes you have to do a further manipulation. So don't forget, when you run into number 5, that's going to happen. Check out the key to see if you've done it correctly. Let's move on to number 6. Number 6 is a building on to the question we just did here. This question is find the molecular formula. Okay? Now the molecular formula is how the molecular compound actually exists in nature. Now how do we do this? Well, we've done the percents. From the percentages that we've got from independent laboratory practices, we got the what? The empirical formula from doing the work that we just did. Now with the empirical formula, okay, already at hand from this laboratory analytical process, we are now going to build and see what the molecular formula is. As we're going to see in AP next year, or maybe this year, there are going to be some laboratory techniques where we can actually come up with the actual molecular mass, or the molecular formula. So loaded with an empirical formula from a one type of analytical procedure from percentages, we're going to now determine the molecular formula, as long as we have the molecular mass. The molecular mass would have to come from another type of experimental procedure. So using multiple procedures loaded with the molecular mass and knowing the empirical formula, we should be able to build or determine what the molecular formula is. So here's how I go ahead and do it. I call it the box method. Okay, and here's how I do it. I build myself kind of a crisscross box. Now if you want to enclose the box you can, but I'm just going to leave it like that, so really there's a box here if you like. Okay, now what I have up top is I have the molecular information, and then below I have the empirical information. Okay, so loaded with the empirical formula, I know the empirical formula is CH3. I'm going to find the empirical mass. So this would be the mass area. And this would be the formula area. Formula. Okay, so I know that, well, 1 carbon is 12 from the periodic table, and 3 H's are 1 apiece. So 12 plus 3, this gives me 15. 15 grams. Okay, so I just found the empirical mass. All right, well, they told me already that the what? That the molecular mass is 30 grams. Well, look at this. For me to go from 15 to 30, that's a multiple of 2, a whole number. Well, my friends in chemistry, whatever I do to this side, I have to do to this side. So this is a multiple of 2. 2 times 1 carbon is C2, and 2 times 3 what? H's is 6 H's. And if you want to verify if this adds up to 30, you can do that. 2 C's. 2 times what? 12 is 14. I'm 24. That's creative math, I guess. And then I have 6 H's. 6 times 1 is 6. Lo and behold, you've got a nice check there. So the answer to the question is the molecular formula is C2H6. This multiple that we find will always be a whole number. Okay? Let's do one more to make sure we're on the same page. Okay, so getting a little fast here. I want you to try number 7 on your own. and I'll get back to you. So pause me, please. Pause, pause, pause. All right, so number 7, I get N2O5. You say, whoa, how did that happen? How do I have the same empirical formula as molecular formula? As I told you before, and we started this process, there are some chemicals or compounds that are already in their lowest ratio, and they exist in nature exactly this way. Remember, water is H2O. It's a 2-to-1 ratio. It's already in its lowest formula, so that's water's empirical formula, but it's also its molecular formula. So there are times where the empirical mass will match the what? Molecular mass, and that's telling you that the lowest ratio, the empirical formula, is also its molecular formula. So please try the rest of this. 8, 9, and 10 has a smiley face because I'm combining both types of questions. You have to build the empirical formula first, then do its molecular formula with the box question. So hope you enjoyed that. If you're not, sorry, I feel bad. I'm over it. Look at the key to review.